All right, we're going to start chapter 7. Chapter 7 deals with Newton's third law. And we have to remember Newton's three laws. We talked about them before. Shorthand notation. One, it's inertia, which just says that any object wants to maintain its state of motion, whatever that is. Okay? Whether it's at rest or whether it's moving, it wants to continue moving in a straight line, or it wants to stay at rest if it's at rest. To change that inertial state, you have to apply a force. And the force creates an acceleration, and that acceleration changes the inertial state. 3 is what we call the equal and opposite. Meaning to every force that you, every force that you create, there's always an equal and opposite force. No matter what, there's an equal and opposite force, which is what we're going to talk about in this one. So, what that means is, or our rules for this, is the forces have to be equal in magnitude to be a third law pair, opposite in direction, and they have to be on two different objects. That's the one that most people make a mistake on, is they say, oh, two of these are equal and opposite, but they're not on a separate object. For example, I've had people tell me that, oh, here's a box sitting on a table. And if I do a free diagram of a box, I say, oh, I got gravity, and then I have a normal force. Well, those forces are equal and in opposite directions, so they're a third law pair. But they're not, because both of those are forces on box A. They're not on different objects. Technically, the normal force is the force the table is applying to block A, and block A would apply a force to the table. So if you did a free body diagram of the table, you'd have to have force of block A on the table, which would be exactly equal and opposite to the normal force. But we're not doing a free body diagram of the table. Same thing with gravity. There's always an equal and opposite too. Meaning Earth, all of the mass of the Earth, is pulling on block A with this amount of force. Equally, block A is pulling on the Earth with that same amount of force. But we're not going to do a free body diagram of the whole Earth. That would be way too complicated. So these have equal and opposites. They don't show up because we don't do the free body diagrams of the item that has the opposite force. So be careful about that. This is the critical thing right here. Also in chapter 7, we deal with ropes. And let's say you have a block A, you have it connected to a rope, goes over a pulley, this is my pulley here, to block B. We're going to assume in chapter 7 and chapter 8 that all pulleys are massless and frictionless. So the pulley essentially doesn't do anything. All it does is it changes the direction of the force. And what we're going to say is, let's do a free body diagram of box A here. And then we're going to assume B has greater mass than block A. So MA times G. This is the free body diagram of block A. And then we got tension going this way. Okay? And then over here for block B, this is block A. For block B, we're going to do a free body diagram. But the mass of block B is much bigger than the mass of block A. But notice, I'm going to draw this because the tension needs to be the same. That needs to be the same magnitude. I might get a little higher. Why? Because when you have a rope and you pull on the end of the rope, what's the other end of the rope feel? They feel exactly whatever pull you pull on this side. So whatever tension I create on this side, the other side is going to feel that exact same force. So the tension on one side of the rope is going to be equal to the tension on the other side of the rope. And so those tensions have to be the same. Okay? Notice though that the weight here, the force of gravity on B, is greater than the tension, so block B is going to accelerate downwards. But over here, the tension is the same size, but block A, the weight of block A is less than the tension, so this block is going to accelerate up. Let's talk about acceleration constraints. If the two blocks are connected by a rope, they must have the same acceleration. Two blocks connected together by anything must have the same acceleration. All right, that's pretty much just saying, okay, these, because they're connected together, have the same acceleration, because whatever I do to this one, it's got to make that one do exactly the same thing, or vice versa. So the two blocks connected must have the same acceleration. But that changes things. So let's look at this. Let's say I have a block here, block B, and it's pushing block A, and I got my hand here. This is my hand. And I'm pushing block B, or I'm applying a force in this direction so that both block B and A are accelerating. I'm just pushing the two blocks across the table or floor, whatever it is. Block B and block A are both accelerating. Not only are they accelerating, but they're touching each other, so they have to have the same acceleration. But if they have the same acceleration, does that mean they have the same net force? Well, let's think about it. For block B, so F net x for block B, it's got to be equal to mb times A. That's Newton's second law. And for block A, F net in the x direction of block A is equal to ma times A. Where's the net force coming from? It's coming from your hand. But do they have the same net force? The answer is no, because the acceleration is the same. That's why I didn't put any subscripts there. But if this has less mass, then this number times the smaller number is going to give me a smaller net force than this number times a bigger number would be a bigger net force. Okay? And it's the sum of the net force on block A and the net force on block B that has to equal to the force I'm giving it as an impulse. So, be careful. Just because they have the same acceleration, they do not have the same net force acting on them. You have to think about that. Conceptually, it makes sense once you think about it, but it's not obvious right from the get-go. Okay, with that in mind, we can do pretty much all the problems in Chapter 7. So next thing I'm going to do is do some problems in Chapter 7 as examples.